its own structure. That's the, okay, right. And once you define in space, once you generate in space an electric field, for instance by generation through electric charges and so forth, the electric flux through a given surface is an interesting quantity to consider, very relevant for electromagnetism, very important. It is analogous to the intensity of the wind, which blows through a surface, through a window. If you open the window and it's stormy outside, you get hit by the wind with various intensities, right, in different ways. And of course, the way you get hit by the wind through the window depends on the angle of the wind direction with respect to the perpendicular direction or normal direction on the window, of course. This is exactly the analogy, if you want, to explain this idea of flux of the electric field through the surface. And you might have heard about Gauss's theorem, which relates the total value, the value of the total electric flux through a closed surface, like a sphere. It's very easy to calculate, and it turns out simply to be that the total flux is proportional to the total electric charge Q inside this closed surface, which is an ideal surface, right? It's an imaginary surface. It can also be an imaginary surface through which you want to calculate the flux. Now, what's that now? I can't remember. Oh yes, well, the science of electricity and so forth has undergone many steps. And in an hour, or even in 2 hours, it's not very realistic to describe all these steps. But, of course, important concepts to mention are electric potential energy. That's important, because from that we get to electric potential and to the electric potential difference between 2 points in space. The electric potential is analogous with the gravitational potential. It's very analogous as far as electricity is concerned, because the electric force is conservative, you see. The work, mechanical work done by the electric force to displace an electric charge from point A to point B is independent of the trajectory. Seems quite magical, but it's true. It's very simple, but it's fundamental. The work is, and so it depends on what? If it doesn't depend on the trajectory, well, it just depends on the initial state and the final state. As this work is an energy, you have to imagine a form of energy linked to the initial point and the final point, and that is what we call potential energy. So you can speak of potential energy in physics if you have conservative forces somehow. Otherwise, if the force is not conservative, like the magnetic force, the Lorentz force, for instance, and so forth, there is no magnetic potential energy, classically speaking. We only have an electric potential energy. There's another apparently profound difference between, you see, magnetism and electricity. And so you can define U, which is the potential energy expressed in joules, V, which is the ratio of potential energy over the value of the charge Q, which undergoes this displacement. In volt, 1 joule over 1 coulomb is 1 volt, so you can define 1 volt as, you see, the energy that would be acquired by an electric charge, okay, of 1 coulomb, and so forth and so forth. And the potential difference is obviously related to the work done by the electric force. Okay? And to assign These are classical concepts, but very important ones, because you see, all of electronics and electricity is constructed on that. Then, this is another chapter which you might remember. How do electric charges distribute themselves on conducting bodies, conductors? What is a conductor, by the way? I haven't said that, but you all know it, but we have to say it. A conductor is an object into which the electric charges are able to move easily, right? A dielectric or dielectric is the opposite, right? Is an insulator, an isolator, I think. The dielectric substance or body or object is an object into which the electric charges can't move easily. Then we speak also about semiconductors, which are fascinating and technologically speaking, extraordinarily important substances, which have very interesting electronic properties, which of course you can't understand fully with classical electromagnetism and physics. You need, guess what? Quantum physics to understand the electronic structures of the material. And these semiconductors are wonderful things because, as you know, they are at the heart of the transistors, electronic transistors, which is the central component of the chips for computers. So all of computer science, everything is at least related to the quantum properties, quantum electronic properties of semiconductors. That's computer science. We need quantum physics, remember. And then you see, you have the concept of electrostatic equilibrium, which tells you that if a charged conducting object is in the state of electrostatic equilibrium, the charges have to distribute themselves on the external surface. There's no net electric field inside the conducting object. You know about Faraday's cage experiment and about Coulomb's theorem, which tells you where the highest density, superficial density of electric charge is on these conducting pieces of elements. You know, you've heard about the electric winds. You know that the density, the surface density of electric charge is very high where you have strong curvature points of the bodies. So if you have a charged needle, a piece of metal needle, and you bring it close to a candle, a lighted candle, you see that the flame is undergoing a wind. It's called the effect, of a wind, of the electric wind. Because a strong electric charge at the point of the needle induces in the air the formation of ions or something like that, and they in turn undergo electrostatic repulsion from the needle. So there's an air flux generated by this phenomenon and so forth and so forth. It's all very nice and very interesting. But I have to go on to say something about dynamical electricity. Right? As this has been discovered essentially by Galvani, Volta and others abroad. It started with bioelectricity, if you want, by electricity in living beings, or manifested by pieces of living beings. And we have things which are quite simple but fundamental, which you all know. What is electric current? What is electricity in the sense of electric current in a conducting piece of wire? Right? Well, it is a global, well-ordered motion of electric charge, or electric charges. And usually in metal wires, the electric charges which are moving are electrons which have been discovered in the 19th century already, I think, by Thomson. Thomson proposed a first sort of atomic model of the atom, which you all know to be the plum pudding, as we say in English, in England. The plum pudding model of the atom, which is called a modello panettone in Italy. Anyway, it's a cake. It's a dessert atom in all the countries, I guess. And the essential thing is that the electron carries the unit of electric charge. You all know the value in Coulomb of the electric charge of the electron, don't you? It's minus 1.6 10 to the minus 19 Coulomb. Very small value in Coulomb. And, you know, I have to go quite quickly through this because these things are things you know, or you can easily find. This is the definition or the concept, if you want, of intensity of electric current, which corresponds to the quantity of electric charge which flows through a section of a conducting body, transversal section, per unit time. So it's expressed in ampere. 1 coulomb over 1 second is 1 ampere. And so forth. What can I tell you? Well, we have an infinity of things, of course. All of electronics has its basics and roots here. You have the law of Ohm, which relates the potential difference to the electric current which is generated and which introduces the concept of resistance, right? You know about one interesting and funny thing. In order to remember and study well the law of Ohm and all of these things, hydrodynamical analogies are very simple and useful. Electricity seems to behave just like a flux of a fluid. You can understand here it's a flux of water in the analogy, and in reality we have a flux of electrons, tiny electrons, electric charges. But you can simulate resistances and so forth, and Kirchhoff joining points and generators, because if you want a permanent electric current, you have to spend energy, unfortunately, we have to pay. And you need a pump of some kind, which brings your particles from the lower potential again to the higher potential, and water from the lower level to the higher level. So you have to spend work again, and so forth, and so forth, and so forth. How much time have we left? We know the hour. 25 minutes. Mm-hmm. Okay. So, this is the Joule effect. Electric current generates heat because the electrons, or the charges which flow through a material, undergo collisions with the particles which compose that material. And the collisions causes the motion of these particles. And motion of the particles means thermal heat. I mean, it is heat, which is thermal energy, which is kinetic energy of the constituent particles. So you can understand why you can dry your hair with these devices in part, why electric kitchens are working, and so forth, and so forth, and so forth. Well, this is something about another device which you can imagine. Charge accumulators or condensators are a very important part of electric devices. They can explain how the flash works of photographic machine, because you need to accumulate electric charge and then to discharge it all of a sudden. And the physical properties of condensators are also explaining how the keyboard of a computer works, because when you press on a key of the keyboard, you vary the distance between the two plates of a condensator. And varying the distance, you vary the capacitance of the condensator. And if you vary the capacitance, you vary the quantity of electric charge or the potential difference, and so forth and so forth. And this generates a signal which generates ultimately on the screen a symbol.